Welcome to Unacademy, the largest online e-learning platform, and welcome to Circuit Theory Crash Course, Lecture 8. We are dealing with the resonance. Before that, let me tell you about myself. I am Vice SRAVAN Kumar, having 7 plus years of teaching experience and mentored more than 5K students for GATE and engineering services and also cracked GATE. Let me also explain you about the Unacademy installation procedure app, Unacademy Learning app. Type it in Google Play Store. Then click on this install. Then you will have gate and engineering services if you are opting for. Then click on this plus and click on this get plus subscription. You have both iconic and plus subscriptions. You'll get a dedicated mentor for this. You can use my code as YSK10 to get maximum discount and click on this proceed to pay. You have many payment options like debit and credit cards, EMIs, UPIs, wallets, net banking. Using any of these platforms, you can get subscription to Unacademy, the largest online e-learning platform. Unacademy Combat is the largest fortnightly competition for GATE and best questions by the best Unacademy educators. Unacademy has brought the Combat, Unacademy Combat, the challenge questions curated by the best Unacademy educators. The questions guaranteed to keep the test engaging, challenging, and fun. It is a super fast and fun with real time ranking. See how you rank against the others with a live leaderboard after every question. So compete with the best. Know where you stand among all other contestants. So detailed solutions by top educators. Get in-depth video solutions for their questions right after the contest. And you have scores, leaderboard, rating, and awards. So compete, crack, and conquer. Now compete with the best and win the amazing prizes like Apple MacBook Air as the first prize and Apple iPad Mini as the second and Apple AirPods as third prize and rupees 1000 Amazon vouchers for top 100 rankers in this competition. Now, Unacademy Combat, as I have told you, let us summarize it's India's largest fortnightly competition for GATE, challenging GATE questions created by our best educators and super fast and fun with real time ranking, compare with the best and detailed video solutions by the top educators. So win exciting prizes as I told you for the first, second, third and the top 100 rankers. You have Apple MacBook Air, Apple AirPods, Apple iPad Mini and rupees 1000 vouchers. So enroll for free December 16 6 p.m. Register now for Unacademy Combat. Coming to circuit theory crash course, today's topic is resonance and that we are continuing today. We are continuing this resonance. I'll just give you a brief idea of what we have done in the previous session. Srinivas, hi. Raju, good evening, sir. Good evening, Raju. Good evening, Soumya. So, what was resonance is any circuit is said to be under resonance if its voltage and current are in phase. If the applied voltage and current are in phase. Ramchandra Kumar, good evening. Welcome to Circuit Theory Crash Course. Or whenever voltage and currents are in phase, power factor is unity. So cos phi is 1 because V and I, if they are in phase, the phase angle is 0 and cos phi is 1. So this is what we have discussed yesterday. Also, I told you about series resonance circuit or series resonance. We have an R, L, C in series with an applied voltage Vs. You have R, L and C. This is XL and minus JXC. And we have found what is F naught is equal to 1 by 2 pi. Eagerly waiting for this topic. Thank you, Ramchandra Kumar. 1 by 2 pi root LC. Also, we have derived expressions for bandwidth as well as lower and higher cutoff frequencies. So I just want you to add something here. There are students asking me about the quality of the video. Quality of the video. Let me tell you, you have the screen that you are watching here, and in the top right corner you have three dots. Click on them. Click on this, you'll have a pop-up here, and if you click on that, you'll have a pop-up. That pop-up will have something like a report as the first one, and second is the quality, and also you have some other things. Click on this quality. There is another pop-up like auto 144p and 240p and 360 and 480. If you click on this 480, you will be able to see the live session very clearly. So once again, I just want to repeat this. Students were asking me about the quality. You have to click on your screen. This is the screen that you are watching. Either it's a laptop or a it's mobile phone. In mobile phone you'll have three dots. Click on these three dots, you'll have a pop-up wherein you'll find reports, quality, and some other things. Click on this quality. There is something called as auto 240p 360p 480. Click on this 480, then this video quality will be good. So that is the setting that you have to do. Ajay Kumar, good evening. Karthik, good evening. Welcome to Circuit Theory Crash Course. So just do this. Click on 480p in quality so that it will be more clear for you, the video quality. So let's continue with this discussion of series resonance. So let us continue that discussion. Now today we will be looking at the series circuit has a supply voltage Vs and a resistance, inductance and capacitive reactance with current. We have written the impedance as R plus J into XL minus XC. R plus J into XL minus XC. Vishwaja, good evening. Anup, good evening. Welcome to Circuit Theory Crash Course. So this is the value of Z impedance, and under resonance XL is equal to XC. Therefore, Z is equal to R. When you equate this, you'll be able to find F naught, that is 1 by root over 2 pi root over LC, or omega naught is equal to 1 by root over LC. Nagesh, good evening. Welcome to Circuit Theory Crash Course. Now, let me tell you about, because you have a resistor, inductor, and a capacitor. There is some voltage across resistor, voltage across inductor, and voltage across capacitor, and there is also a supply voltage Vs. Now, what is the voltage variation of this voltage across inductor and voltage across capacitor with frequency? That is what we'll be looking at. Now, I'll write both the expressions for voltage across inductor. VL is equal to I into JXL, and VC is equal to I into minus JXC. Mahesh, good evening. Welcome to Circuit Theory Crash Course. Today we are discussing resonance continuation. In the previous session we have started resonance. So today we'll be discussing what is resonance quality factor specific in today's topic. So VL is equal to I into JXL and VC is equal to I into JXC or X. So you can write VL is equal to I into, what is I? V by R square plus XL minus XC whole square under root into JXL. Similarly, VC is equal to V by under root R square plus XL minus XC whole square into minus JXC. Now coming to Now let us see the variation of voltage across inductor and voltage across capacitor. This is the applied voltage. Now if you draw voltage across capacitor, it would be something like this. And if you draw voltage across inductor, it would something be like this if you are varying. And this point of intersection, this is voltage across inductor and voltage across capacitor. This point of intersection of this is the frequency, resonant frequency. And the frequency at which this voltage across capacitor is maximum is the frequency, capacitive frequency, and this is FL, the frequency at which, and this at this point VL is equal to VC, and this is the frequency at which voltage across capacitor, this is VC curve, this is VL curve. So in this region it is behaving like a capacitive, and in this region it will be behaving like an inductive circuit. So let us see. Now voltage at frequency 0, the voltage across an inductor is 0. Now at frequency 0, voltage across a capacitor is the equal to the applied voltage. And from graph, if you observe, voltage across inductor and voltage across capacitor are greater than the supply voltage. This is Vs. So that is the reason series resonant circuit is called as a voltage magnification circuit. It is called as a voltage magnification circuit. It's also called as a voltage magnification circuit. Now how do you find these frequency FC and FL are? What is the frequency at which the voltage across capacitor is maximum, or FL is the frequency at which the voltage across the inductor is maximum. Almost these will be at this point. Now the other important point is at resonant frequency, voltage across inductor is equal to voltage across capacitor. There will always, Manohar, good evening. There will always be a energy transfer between the inductor and capacitor, and the heat is dissipated in the resistor at resonance. Now how do you find this FC and FL? Although I'm not going to derive it, I'll just give you how to do that. That is to find FC and FL. Now consider voltage across inductor. VL is equal to I into JXL, or I into XL. What is I? V by root over R square into XL minus XC whole square into XL if you consider the magnitude. Differentiate this VL with respect to frequency and equate it to 0. When you equate it to 0, you can find the FC as 1 by 2 pi root LC 1 minus under root of 1 minus R square C by 2L. So this is the frequency at which the voltage across the capacitor is inductor is maximum. It is 1 by, let me write this once again. Yeah. So it is 1 by 2 pi root LC under root of 1 by 1 minus R square C by 2 into L. So similarly, if you try to find FC, consider VC is equal to I into XC. I is V by root over R square plus XL minus XC whole square into XC. Differentiate this VC with respect to frequency and equate it to 0. Differentiate this VC and equate it to 0. You'll find FC is equal to frequency at which capacitive voltage is maximum is 1 by 2 pi root LC into 1 minus under root of 1 minus r square c by 2l. This is a frequency at which voltage across the capacitor is maximum, and this is the frequency at which voltage across the inductor is maximum. That is found by differentiating this and equating it to 0, and differentiating voltage across capacitor and equating it to 0. Thank you, Mahesh. Nice explanation. Thank you so much. So with this, we'll introduce what is quality factor. What is quality factor? What is a quality factor is, it is the ratio of the maximum energy stored in the circuit to power dissipation per cycle. So this is the quality factor denoted by Q or Q naught or Q. So Q is equal to, so it's the ratio of maximum energy stored in, in a circuit to the power dissipation per cycle. Now the maximum energy stored is given by W is equal to half L I square, or L maximum, L into I maximum square. This is the maximum energy. And power dissipation per cycle is given by, power dissipation is I square R, per cycle is 1 by omega. So power is equal to I square, I is IRMS by root 2 whole square into R into 1 by omega. So from this you can write what is quality factor Q is equal to, quality factor Q is equal to half L Im square by, it is Im by root 2 whole square into R into 1 by omega. Now if you just simplify this, you can get omega L by R. So quality factor is equal to omega L by R. If you substitute, this is inductor energy. If you substitute the capacitor energy, you'll also get quality factor is equal to 1 by omega CR. So this is the expression for quality factor. This is the expression for quality factor. Once again, we'll just see quality factor is the ratio of, quality factor is the ratio of maximum energy stored in the circuit to the power dissipated per cycle. Maximum energy stored in the circuit to the power dissipated per cycle. Maximum energy stored is half Li square or half CV square, and power dissipated per cycle is I square R into 1 by omega. I square R into 1 by omega. This is I RMS, that is I maximum by root 2 whole square into R into 1 by omega. Vijay Gaud, good evening Vijay Gaud. Welcome to Circuit Theory Crash Course. We are discussing resonance topic today. So with this, if you substitute half Li square and Im by root 2 whole square into R into 1 by omega, if you cancel out these, you'll get omega L by R. Omega L by R. So now let us also look at what is quality factor in terms of voltages. You can also write quality factor as quality factor Q is equal to, quality factor Q is equal to reactive component by the active component. Reactive component to the active component, it is IL by I or IR, or it's also equal to VL by VR, or you can also write it as IC by IR. So this is initiative teaching methodology. Thank you, Vijay God. So this is also the quality factor. You can define in this way. And let's also look at one problem that we will solve uh, on the series resonance. Then I'll be discussing about parallel resonance today. So this is the quality factor. So you can also write it as Q is equal to voltage across inductor I naught into XL naught by voltage across resistor I naught into R. So this is XL naught by R. What is XL naught? Omega naught L by R. So quality factor is equal to omega naught L by R, that we have got in the previous one. Omega naught Q naught is omega naught L by R, or Q naught is equal to 1 by omega naught CR. So these are the expressions for the quality factor. So we have also defined quality factor. We have seen, let me write what we have done till now. Yeah. So we have found what is the capacitor, what is frequency Fc, and what is Fl. It is a frequency at which voltage across capacitor is maximum, and it is a frequency at which voltage across the inductor is maximum. And we have found what is quality factor. It is omega naught L by R, and Q naught is equal to 1 by omega naught CR. Or also you can write it as voltage quality factor is equal to VL by VR or VL by VS, and you can write voltage, or you can also write it as VC by VR or VC by VS, and you can write quality factor voltage across inductor is equal to Q naught into Vs, or voltage Q naught into Vs. So these are some of the expressions for the quality factor. Now let's look at one problem. Let us take one question. I am taking one question from Ravish asking a series RLC circuit. A series RLC circuit. Mahesh Reddy, good evening. Welcome to Circuit Theory Crash Course. A series RLC circuit has R is equal to 10 ohms and L is equal to 0.01 Henry and C is equal to 100 microfarad. And the question is find resonant frequency. This is one of the exam from the previous university question papers even. Resonant frequency, bandwidth. I'll give you all the expressions. I want you guys to tell me the values, bandwidth, and lower and upper frequencies. So the question is given like this, and you need to solve this with solution. So let's consider the expressions for each and everything. R is given as, first you need to write the values. L is given as 0.01 Henry and C is given as 100 microfarad, or it is 100 into 10 power minus 6 farads. So what is the first one? Resonant frequency. It is a series RLC circuit. So F naught is equal to 1 by 2 pi root LC. So you can substitute 1 by 2 pi. Under root of L is 0.01 into C is 100 into 10 power minus 6. I want you to tell this answer. Now let us consider the second one. That is, first one is frequency, second one is bandwidth. Bandwidth is equal to R by 2 pi L. What is R? It is given as 10 by 2 pi into L, value is 0.01 Henry. And tell me the value of this. SR, good evening. Good evening, SR. Making topic quite interesting. Thank you, Vijay Gaud. Vijay Gaud Gauni. So third one is lower and upper cutoff frequencies. We know F1 is equal to F naught minus bandwidth by 2, and you can substitute that value. You will find F naught here and bandwidth here. And what is F2 is equal to F naught plus bandwidth by 2. Substitute these values. I'll tell you what are the values that you get. So F naught is equal to 159.1 hertz and bandwidth is 159.15 hertz even. And if you find f1, it is 79.58 hertz, and f2 is 238.73 hertz. So this is the these are the values. So the question, once again, I'm reading the question. The question given is a series RLC circuit has R value, L value, and C values are given, and we are asked to find what is the resonant frequency, bandwidth, lower and upper frequencies, upper cutoff frequencies. So we have taken F naught is equal to 1 by 2 pi root LC, and bandwidth R by 2 pi L, and lower and higher cutoff frequency expressions, and found these values. Hope this is clear for you all. This is one problem on series resonance. Let me also take one more, and then we'll start about parallel resonance. So let us consider one more question that is given for us. There is a question like this. The question says, the question is, a series RLC circuit, a series RLC circuit has a quality factor of, has a quality factor of 5 at 50 radian per second. The current flowing through the circuit at resonance is 10 amperes. The current flowing through the circuit at resonance is 10 amperes. Supply voltage is given, that supply voltage is 100 volts. Find circuit constants. Nothing but the values of RLC. So you need to understand this question first. The question is quality factor is 5, so Q naught is equal to 5 at frequency 50 at omega, because radian per second is omega, so at omega naught is equal to 50 radian per second, and current flowing is given as 10 amperes, and supply voltage is given as 100 volts. Now what are the constants that you need to find? We know I naught is equal to current V by R, because under resonance, resonant current is V by Z, but Z is equal to what? R plus J into XL minus XC. XL is equal to XC indicates Z is equal to R. Therefore current I naught is equal to V by R. So V by R, what is V? 100 by R value. You do not know R value, but you know what is current. So this implies what is current value? 10 is equal to 100 by R. This will give you the value of R. R is equal to 100 by 10, so 10 ohms. Now let us consider the next one. Next, you need to find, we have found R, you also need to find L and C. In order to find L, you need to consider omega naught is equal, sorry, you need to find L. Q naught is equal to omega naught L by R. Quality factor Q naught is given as 5 and omega naught as 50, and L we already got value of R, so 10. So L is equal to 10 into 5 by 50 is equal to 1 Henry. So this is the value of the inductor that is given to us. Sorry, this is the value of inductor that we got from the given parameters. And let us also find the third parameter using quality factor Q naught is equal to 1 by R root L by C. So Q naught is given already. What is Q naught value? Q naught value is 5 and 1 by R value is 10, L value is 1 and C. So if you simplify this, you'll get the C value as 400 microfarad. Anup Sagar, clear? Thank you, Anup Sagar. So this is the value of C. So once again, I'll read the question. The question given is, a series RLC circuit has a quality factor of 5 at 50 radian per second. The current flowing through the circuit at resonance is 10 amperes. And the supply voltage is given as 100 volts. Find the circuit constants, which are nothing but RLC. Now use this expression of I naught is equal to V by R. I naught is given, V is given, and R is not given. So you'll get R from this. Then you can consider the quality factor expression. Second, omega naught L by R. From that you'll get the value of L, because you already know R value, omega naught is given, Q naught is also given, you'll get the value of L. And Q naught is equal to 1 by R root L by C. You must have a doubt, why, how did we get this? You can just consider Q naught is equal to omega naught L by R. What is omega naught? F naught is equal to 1 by 2 pi root LC. If you take 2 pi here, 2 pi F naught is equal to 1 by root LC. What is 2 pi F naught? Omega naught. Therefore, omega naught is equal to 1 by root LC. Omega naught is equal to 1 by root LC. So if you substitute this, omega naught is equal to 1 by root LC. Substitute omega naught is equal to 1 by root LC into L L by R. So what is this? 1 by root L into root C into L. L root L times by R. So this is 1 by R. It's already root L by C. So Q naught is equal to 1 by R root L by C. That is the expression I have used here. Base level teaching is very useful for me, sir. Thank you for Unacademy and SRAVAN, sir. Thank you, SR. So Q naught is equal to 1 by R root L by C. That this is how we got the expression, and we have substituted here and got the value of C. So hope you are clear with these two problems that we have done now. One is RLC is given and finding the F naught bandwidth and F1 F2, and the other question is given Q naught omega naught I and V, we have found R, L and C values. These are the two most frequently asked questions in university examinations. So we have done with series resonance. Now let us discuss what is parallel resonance with one circuit. You also have many circuits for parallel resonance, uh, but let's consider one circuit. Parallel resonance. I'll consider this circuit with a resistor, a supply voltage, with a coil, that is resistor and inductor, and a capacitor. So this is the supply voltage Vs, this is capacitor Xc, and this is R, and this is XL. Now we'll write the impedance first. Impedance, let us call this impedance as Z1. So Z1 is equal to R plus JXL. Let us call this impedance as Z2. Z2 is equal to minus JXC. Now we can write admittance. Total admittance is equal to Y1 plus Y2, where Y1 is equal to 1 by Z1 and Y2 is equal to 1 by Z2. What is Y1 is equal to 1 by Z1 is equal to 1 by R plus J into XL. Rakesh, hi, good evening. Welcome to Circuit Theory Crash Course. So you multiply and divide by R minus JXL, component dividendo, you'll get R minus JXL by R plus JXL into R minus JXL. It is R square plus XL square. Because we have to separate real and imaginary parts, we have done this. And you can also write Y2 is equal to 1 by Z2, that is 1 by minus JXC. If you take J to the numerator, it is J by XC. So Y1 and Y2, we are writing admittance instead of writing impedance, because we have two parallel impedances here. So now write total admittance. Y is equal to Y1 plus Y2. Y1 plus Y2. Now if you write the total admittance Y1 plus Y2. So what is Y1? Y1 was, let us consider R minus JXL by R minus JXL by R square plus XL square, plus what is Y2? It is J by XC. Now write real and imaginary parts separately. R by R square plus XL square minus JXL by R square plus XL square plus J by XC. Still further you can write R by R square plus XL square minus, if you take j common, let us take plus j common. So 1 by xc minus xl by r square plus xl square. So for this, any circuit to be under resonance, for any circuit to be under resonance, the imaginary part must be equal to 0. This part must be equal to, made equal to 0. This part must be made equal to 0. Now if you consider that, I'll just take this part to the next slide and make it equal to 0. And let us take this is equal to 0 because the imaginary part must be equal to 0. So you can write it as xl by r square plus xl square is equal to 1 by xc. What is xl? We already know xl is equal to omega l and xc is equal to 1 by omega c. So you write omega l by r square plus omega l whole square is equal to 1 by xc, 1 by omega c. So it is omega l by r square plus omega square l square is equal to omega c. You can cancel this omega. This is under resonance. So you are writing anti-resonance. Parallel resonance is also called as anti-resonance. So I have taken AR. Now this is L by R square plus omega AR square L square is equal to C. Now multiply this. L is equal to CR square plus omega AR square L square. Now just write omega AR square L square is equal to L minus CR square. Now what is omega AR square is equal to L minus CR square by L square. Omega AR square is equal to this. So you can write 1 by L minus CR square by L square. You can write this omega AR square is equal to. From this you can write omega AR square is equal to, omega AR. We'll write it as omega AR. So omega AR is equal to root over 1 by L minus C into R square by L square. You also have a C here, omega A square L square. So omega A R square L square C. So this is L square C. This is 1 by LC minus L square C. C gets cancelled. So you don't have a C here. So you don't have a C here. And you have 1 by LC minus R square by L square. So this is the expression for, a parallel circuit, parallel resonant circuit, the frequency. So furthermore you can also write it as, omega AR 2 pi f AR is equal to under root of 1 by LC minus R square by L square. You can write f AR is equal to 1 by 2 pi root over 1 by LC minus R square by L square. So this is anti-resonant frequency, or the resonant frequency of a parallel circuit. Resonant frequency of a parallel circuit. Hope this is clear. What have we done? I'll just tell you. We have considered a circuit with a coil. This is a coil in parallel with a capacitor. We have written the impedance of the two branches, and then we have considered the admittance because it's very easy to calculate that. Then we have made real and imaginary parts separate. Then I have made this real part and imaginary part as separate. And under resonance this is equal to 0. So you'll get only Y anti-resonance is equal to R by R square plus L square. From this you can write Z anti-resonance is equal to R square plus XL square by R. This is called as the dynamic resistance. This is called as the dynamic resistance. We'll use this once again. We'll also use this once again. So this is you have You have taken this imaginary part, we have considered this imaginary part and made this imaginary part equal to 0. Then on simplification you got omega AR value and FAR value, which is the frequency, resonant frequency of a circuit under a parallel circuit under resonance. So what is if F naught FAR is equal to, what is that we got? FAR is equal to 1 by 2 pi root over 1 by 2 pi root over 1 by LC 1 by LC minus R square by L square 1 by LC. If R is very small than L, if it in case, then FAR can be written as 1 by 2 pi 1 by root LC if this is very small, or omega AR is equal to 1 by root LC when this is the condition. So now let us consider, the impedance. As I told you, what was the impedance? Impedance is the dynamic impedance. What is the impedance? ZD we'll call it as, or ZAR. I have written it as ZAR, or dynamic impedance is equal to R square plus XL square by R, because Y is equal to R by R square plus XL square under resonance. So if Y is this, Z is this value. It is 1 by Y. So from this, at resonance, if you observe at resonance, R square plus XL square is equal to, if you observe here, R square plus XL square is equal to, if you observe this equation, you can write this R square plus XL square is equal to XL into XC. If you observe this, I'll also write this XL by, we know under resonance imaginary part, XL by R square plus XL square is equal to 1 by XC. From this you can write, what you can write, if you can write R square plus XL square, what is R square plus XL square is equal to XL into XC. Just substitute this value here. So ZAR is equal to R square plus XL square by R, or XL into XC by R. What is XL into XC? XL is equal to omega L. XC is equal to 1 by omega C. What is XL into XC? This is equal to omega L into 1 by omega C. You can cancel this and you'll get omega by L. Sorry, this is, you'll get L by C. Omega and omega will get cancelled and you'll get L by C. So what is that XL into XC? It is L by C by R. What is ZAR, or dynamic impedance, is equal to L by RC. In problems, you'll be given a question in parallel resonance circuit and you will be asked to find, what is the dynamic impedance of a parallel resonance circuit. It is L by RC. Then what is the current? If you know the dynamic impedance of a circuit, what is the current? Current under resonance is equal to, current is equal to I naught is equal to voltage by impedance. What is V by L by RC? That is VRC by L, or VCR by L. Therefore current is equal to VCR by L is the current in a parallel resonant circuit. Current in a parallel resonant circuit. Hope this is clear for you. Now let us find the quality factor as well, and also how the impedance curves, admittance curve varies and current varies in a resonant circuit. Now if you consider this impedance and draw the impedance variation with respect to frequency, impedance with respect to frequency. Now let us say this is the impedance Z and this is frequency F. Now as you know, as the frequency increases, if you take this, as the frequency increases, impedance also increases. At a certain point of time, it will be maximum value and it starts decreasing then. So this is impedance is maximum and it will reduce, and this frequency at which the impedance is maximum is called as the resonant frequency, which is FAR. It is the resonant frequency, and this value at which the impedance is maximum is called as ZAR, that is this value L by RC, that is L by RC, this point, this impedance at which the frequency is maximum. Now if you know the frequency is increasing and it is maximum at a given point, what would be the current? Now let us consider the current. The current will be, if this is current versus frequency curve, current will be minimum as the impedance is maximum. As the impedance is maximum, the current will be minimum. As the impedance is maximum, current is minimum. And if you try to plot the behavior of conductance and susceptance, what is BL is equal to 1 by JXL, and what is BC is equal to 1 by minus JXC, or it is minus plus J by XC. What is XC? 1 by 2 pi FC. And if you try to plot them with respect to frequency, if you try to plot Y and with respect to frequency F, then BC is, it is 2 pi F, right? It is directly proportional to, the frequency. And conductance is a constant line which does not change, and inductive susceptance is inversely proportional to frequency. So this is conductance, this is BC, and this is BL. Capacitive susceptance, inductive susceptance. Capacitive susceptance and inductive susceptance. So this is a variation, 2 pi FC. BC is directly proportional and BL is inversely proportional, that is 1 by j omega is 2 pi FL. So BL is inversely proportional to frequency, and here BC is directly proportional to frequency. This is directly proportional, this is inversely proportional to frequency. So hope you have understood this anti-resonant circuit. This is parallel resonant circuit. I have considered Z1 and Z2 and tried to write the admittance, then equate the imaginary part to 0, and then got this expression for anti-resonant circuit. And then we have written what is YAR, admittance at resonance. Only this value real part you'll get because imaginary equal to 0. From that we have written what is dynamic resistance, and also got the expression for dynamic resistance once again. So this is R square plus XL square by R, and we have tried to simplify this, where R square plus XL is equal to XL into XC, just writing this here, and XL into XC is L by C, and L by CR is the dynamic resistance value. So then we have written what is the current expression. V by current is equal to voltage by impedance. Impedance is L by RC, so it is VCR by L. Then we try to plot what is impedance versus frequency and admittance versus frequency. You can also get it from this curve. You can also try to plot the admittance curve first, then or else you can find the impedance curve. If you write this impedance value, Z is equal to Z R square plus XL square by R, which is the maximum value at resonance. And before this, at omega is equal to 0 and at omega is equal to infinity, you will get very less impedance, that is the impedance is minimum, and at anti-resonance the impedance is maximum, and here the impedance here is maximum and the current is minimum, because impedance and current are inversely related. Hope this point is clear, and also you need to remember that this parallel resonance circuit is also called as anti-rejector circuit or anti-resonant circuit. This is also named as anti-resonance circuit or a rejector circuit, or it is also current magnification circuit. The source current and the current across this capacitor and current across this inductor. The current across this inductor is much more greater than the current source current, so we will call this as a current magnification circuit. We should also write the quality factor here. Let us write the quality factor. So the quality factor Q naught is equal to, the quality factor is the measure of current magnification. It is the measure of current magnification. It is the measure of the current magnification in the circuit, parallel resonance circuit. So Q naught is equal to current through inductor or capacitor, current through inductor or capacitor. It is the ratio of current through the inductor or capacitor to the current at resonance. Current at resonance. So Q naught is equal to I C naught by I, or I naught or IR. So Q naught is equal to, what is the current at capacitor? V by X C naught. And what is the current under resonance? It is VCR by L. Just now we have found that VCR by L. VCR by L. Have substituted this here, and when you write V and V cancelled, 1 by X C naught is equal to CR by L, and if you write this, it is omega naught C by CR by L, and furthermore you can write omega naught L by R. So Q naught is equal to omega naught L by R is the quality factor. And at omega naught is equal to 1 by root LC, when R is very small, we have taken this, and if you write that, Q naught is equal to 1 by root LC into L by R, and if you simplify, it is Q naught is equal to 1 by R root L by C. So this is the expression for quality factor. So the quality factor of a parallel resonant circuit. Now let me write the comparison between series and parallel resonant circuit using some terms, using some comparison. I'll just compare this series circuit and a parallel circuit. We will write this series and parallel resonant circuit with some parameters. I'll consider these parameters as First I'll consider the parameter. The first parameter is the impedance, and the second parameter is current, and third parameter is resonant frequency, and the fourth parameter is quality factor, and fifth parameter is what it magnifies. So what is the impedance of a series circuit? Impedance Z is equal to R under resonance. Under resonance, Z is equal to R. And Z here is equal to L by RC. Just now we have done this. Z is equal to L by RC. So this is Z is equal to L by RC in case of a parallel circuit under resonance. Under resonance, series circuit has impedance R and a parallel circuit has an impedance of L by RC. And coming to the current, current I naught is equal to V by R. Current I naught is equal to V by R. And what is the current here? IAR is equal to VCR by L. Current I naught is equal to VCR by L. Now what is the resonant frequency? It is 1 by 2 pi root LC. And what is the resonant frequency here? We can just write this as F naught is equal to 1 by 2 pi root LC. FAR is equal to 1 by 2 pi under root of 1 by LC minus R square by L square. Now coming to the quality factor, Q naught is equal to 2 pi F naught by L, F naught L by R, and here also Q naught is equal to 2 pi F naught L by R, same. And here it magnifies voltage magnification circuit, and this is a current magnification circuit. This is a voltage magnification circuit and this is a current magnification circuit. So let us try to solve one question that is given in one of the textbooks of Ravish R. Singh on this parallel resonant circuit. So what is the question is, the question says, so this is also one of the university examination questions, a coil of 20 ohms has an inductance of 0.2 Henry and is connected in parallel to a capacitor of 100 microfarad. These are the things given and we are asked to calculate frequency at which this circuit will have as a non-inductive, will behave as a non-inductive circuit, and also find dynamic resistance. This is the question given to us. This is the question given to us. We are asked to find these things. Let us see what are the things that are given to us. The first thing is the coil has a resistance and an inductance. So we have a coil with resistance and inductance which is connected in parallel to a capacitor. This is a parallel resonant circuit. And what are the values that are given to us? The resistance is 20 ohms, inductance is 0.2 Henry, and capacitance is 100 microfarad. And we are asked to find frequency at which the circuit will behave as a non-inductive. That means resonant frequency. That means we are asked to find resonant frequency, that is 1 by 2 pi under root of 1 by LC minus R square by L square. Just you need to substitute the values of R, L, C and you will be able to find it as 31.83 Hertz. And the other thing that is asked is about the dynamic resistance. What is dynamic resistance? ZAR is equal to L by CR. Substitute L value as 0.2 by 0.2 by C is 100 into 10 power minus 6 into R value is 20. If you substitute this, you will get 100 ohms. Therefore, FAR is equal to 31.83 Hertz and ZAR is equal to 100 ohms. So this is one question that is asked in university exams once, and on parallel circuits. So today's takeaways are, we have seen what is FC and FL, that is voltage Capacitor voltage and inductor voltage are maximum at these frequencies and their variation with respect to frequency. Then I told you about what is quality factor of a series resonant circuit. Then we have solved two numericals based on them. Then we have seen what is parallel resonant circuit, and in parallel resonant circuit what is the resonant frequency of the circuit, and what is the dynamic impedance, how does Z and I vary with respect to frequency. And then we have solved one numerical on parallel resonant circuit. So these are the takeaways from today's session. Hope you have got enough idea about this resonance. We'll be starting the next topic from the next class. So as I always tell you, we have India's number one study channels: Creatrix, GATE, Unacademy, GATE, Unacademy, GATE CE, Unacademy, GATE Telugu, Unacademy, SSC JE, Unacademy Computer Science, Unacademy GATE Questions, Unacademy Electrical Junction, Unacademy Engineering Foundation, Unacademy Pathshala, and Unacademy Semester Exams. Please do like this video, share this video, use my referral code as YSK10 to get the maximum discount, and subscribe to this channel and click on this bell icon to get notification of my classes. And thank you once again. Thank you all for joining this session on resonance second part today. So we'll be starting up with the next session tomorrow. Once again, I wish you all good luck and happy weekend, and thank you all for joining me for today's session. Hope you will also join me for tomorrow's session. Anup Sagar, thank you, sir. Thank you, Anup Sagar. Thank you for joining this session on circuit theory resonance topic. And I gave you what are the things that we have discussed today. Once again, thank you all. Thank you for joining the session.